Welcome to lecture number 3 of module first, and this is also last lecture of this module 1. We have seen in module 1 of lecture 1 that what is the evolution of the power system, and then we went on looking at the milestone, and finally we saw the interconnections. That is very important, and the present day power system is highly complex and it is highly interconnected power system. In lecture 2 we saw that the various power system operation and control design criteria, in which also we saw the various states of the power system, such as your normal states, alert state, restorative states, and your extremis or emergency states as well. In this lecture we will see the various control functions of energy management centers. Along with, we will also see the various control hierarchy that is applied in the power system. Here, this is a block diagram of the various functions of modern energy management systems. First, we will see here, we start with the RTUs. RTUs are nothing but the remote terminal units by which we measure the power system data from the field, and this data means this RTU gives information to these various modules and through your telemetry. So this is a telemetry, and the RTUs are the large number in the power system. They are spread all over the world, and they give the various information such that they will give the various measurements, they will give the circuit breaker switch and their status, and with these information we do the various other functions, like we can form the network topology here. This network topology that requires this base system data, that is the intact system information. At the same time, what is the circuit breaker status of the various elements in the power system, the circuit breaker status of the transmission lines, transformers, as well as other circuit breaker status. They are coming to through the telemetry data, and then finally we can have the network topology, means what is the present network information, network diagram. Based on that, this information basically used in your state estimation. State estimation is slightly different than the power flow study, and you know the states of the power system are nothing but your voltage and the angle at all the buses. This is the angle, it is not a power factor angle, it is the bus voltage magnitude angle, and this V is the magnitude of the bus voltages. With the help of these two information, at each bus we can determine all the power system quantities, such as your real power flow, your reactive power flow, and also we can determine the power losses, that is a real power loss, and same time we can go for this reactive power loss as well. So that's why we call the states of the power system. We also determine this voltage and angle in power flow analysis, but in that we normally solve the power balance equations and we get the solutions at the voltage and angle in terms of that. However, in the state estimation, the number of equations are large. However, in the load flow, the number of equations are equal to the number of unknowns. So we get the solution, unique solution at particular condition. In the state estimation, we assume, since we are measuring the data from the RTUs and they are coming through the communication channels, that is through the telemetry information, and these measurements data will have some errors, some noises. So with the help of the various measurements, we normally obtain the voltage and angle that is the best estimate. Means here in the state estimation we do nothing, it is just this error reduction. We have to eliminate the errors as much as possible, so that whatever the information we are getting in terms of voltage and delta, we can say that it's exact information, and based on that we do other online security analysis as well as the economic dispatch, means energy management functions we perform. This state estimation also, if you have determined the voltage and angles, then it can give the various system information in sense that it will give the voltage magnitude, it can give the limit violations, it can give your line flow limits, it can means all the information we can display, and that can be displayed on the computer CRTs or anywhere other display instruments. This state estimation, now the information which we have right now, that is used to check the current operating states of the system. Now the present power system, that's we are measuring the data which is coming through this RTU through this network topology and the state estimation, here the current system operating limits can be checked. Means we can have our system, as already we have discussed in the previous lecture, what are the various states of the power system. Means here we can see whether our voltage, whether your this power flow limits are satisfying, and at the same time we have to go for the load constants, or sometimes we call the equality constants. Means here in the operating limit we check our equality constants and the inequality constants I. Now there's different scenario exist. If we are having there's no violation in the equality as well as the inequality constants, then we can say our system is normal state. If it is not so, means our system may be in emergency state, or it may be in the restorative state, or it may be in extremist condition where both equality and inequality are not satisfying. So then we have to take the control action accordingly. So information here, if it is a normal state, then we have to do other functions. If it is not in the normal state, then we have to give some alarm signal as well, so that the operators can be attentive and they can take the corrective or preventive measures. At the same time, the control actions can be applied at the various points which are required to move the system into the normal state of the power system. Now, if your system is in your normal state, then we can perform the security analysis, and then we can also perform the economic load dispatch. And then this information, the economic dispatch here, it will be passed to the automatic generation control of the power system. Here basically with the AGC, we control the output of generators. For AGC, we require the various information. Those information, that is first one is your system frequency, that is measured from here from the system, from RTUs, and also we require the tie line power flows, because our system may be connected with other neighboring systems. So the tie line power flows are also required in the AGC. So we require the tie line power flow, we require our present setting of the generators, and also we require the security constants with the OPF in this. Then finally we solve our automatic generation control. This automatic generation control will give some signal to the generators. Through again it will go to the telemetry communication, because this whole the process, it is not necessary this process is sitting at the generating station. It may be somewhere else. This is normally in the state load dispatch centers, and these information like your generator settings will pass through the various generators, and then finally we can give this signal, and then we can control, we can achieve our desired outputs. Other here the control actions, if your system is not in normal state, then there's no option. You have to directly control here the various control to bring your system in the normal state. That is, we have to go for the generation excitation control, we have to go to the transmission control, so that we can satisfy your equality and your inequality constants. That's we have to bring our power system in the normal state. Whole this process here, if you'll see, this complete this, which is with the red line here, it is nothing but it is called security monitoring and assessment function. Now you can see here that in detail what we do in this security monitoring and assessment functions of a modern energy management system. Here again, if you see here, the data are measured from this your RTUs. We are getting the measured data. These measured data normally will have the bad data. Bad data may be of two types. Some data that by looking at the data information, you can directly say that this information is wrong. For example, suppose you are measuring a bus voltage at any point, it is your 2 per unit. This shows that your power system it is running, it is not possible, that your voltage magnitude is 2 per unit. Similarly, you can see another information. Suppose a transmission line here, this is giving your circuit breaker here status both end. It is saying that it is a circuit breaker is open, and also it is saying that there is some power flow in this line, which is not possible. So both information are contradictory to each other. So based on these information, we can filter out some of the absurd measurement data, and that is called your filtering of this measured data. Still we have some errors in the measurement due to the communication links, due to the measurements unit itself, due to your CTs and PTs, and those errors we have to minimize in your state estimation function here. This filtering data will give some information for the network topology. Network topology is nothing that we want what is your intact power system right now. What are the various elements those are now in existing and the power is flowing over those lines. So this network topology requires the status of circuit breakers, and then these information can come here. From after filtering we can just this network topology we can form, and this network topology will be utilized in this your state estimation. Again, as I explained, that the state estimation is nothing but we have to determine your this voltage estimate as well as voltage angle estimate. Now again, in the state estimation is a broad process. Here we do sort of analysis. That first one is called the observability analysis, and another is your bad data processing. In the state estimation, the bad data processing means we try to eliminate the bad data. There are so many ways, mathematics behind that, and also we analyze that the observability analysis we perform, by which we can say we can estimate our states accurately or not. So after doing the state estimation, we get lot of information. First, as I said, we are getting the voltage and angle, and by which we can check the operating limits. Limits here your equality constants and your inequality constants, means here we can also call the load constants or your operating constants. If these constants are violating, let's suppose your operating constants for example it is let's suppose is voltage, then we can say we are not in the normal state. So your operating limits, that is your constants, that is your load constants as well as operating constants, then based on that we have to decide where our power system is. Means your power system may be in the normal state, here it is normal state, then you have to perform contingency analysis part. Here this process is called contingency analysis. If your system is not in normal state, it may be either in your emergency control here, or it may be in restorative state. So then you have to perform this restorative control, and if it is in your emergency state, then you have to apply this emergency control to bring your system first in the normal state. Then you can go for the contingency analysis or the security analysis. So it is very important that the security analysis or contingency, this block is called the contingency or security analysis. It is only performed if your present operating system is in normal state. Otherwise, if it is not in normal state, then we have to take corrective action or the preventive corrective action so that we can bring your power system in the normal state. Now you can also see this. Now in contingency analysis, we require several other information. Those are, from the state estimation, we get this load forecast. Normally, whole this process, measurement till all this calculation, etc., it is performed in half an hour interval. So every half an hour we are getting data from the RTUs, and finally we are doing all this process, and again after half an hour we are getting the new set of data. In this half an hour, what happens? Your load, which is keep on changing, that will be varying. So we require the load forecast during that period so that we can have the exact information about the system state within this half an hour. So we require some bus data, bus load forecast, and after getting the load forecast, means we get your P and the Q at the various buses, then that is used in your online load flow. So this is in this online load flow. Here we also require the system states, we require the network topology here, and your other information from the state, so that we can form the external network. As I said, your power system may be connected with other neighboring system, so we have to, it is not possible to go for analysis for all the system, so it is convenient to form that external network, either one or two nodes, and then that is called the external network model. We have to model in such a way that it will not hamper your power system studies. So with this information that is required for your online load flow. We know in the load flow analysis, we require the real power and reactive power informations at the buses, and at the same time we require the network topology here that is coming, and we require the external network, and then we can run the load flow that is used in the contingency evaluation process. Here in this contingency analysis, we will study in this later modules, and it is already I'll discuss one or two lectures on this issue. Now, in this contingency analysis process, your system may be secure or insecure. As I said, in the contingency analysis, security analysis, always we think if any new contingency will occur, whether your present power system for that contingency is well prepared or not. Means your present power system is able to sustain, able to remain in the normal state following any probable contingency that may occur in future, then we can say our power system is secure. So if it is your secure state, then you have to go for here, you can come out and then you can go for this optimal power flow and etc. or so on. If your system is in insecure state, then you have to go for some preventive action, and at the same time you can apply security constraints, optimal power dispatch, because here you are going to control something. You are going to change the settings of some of the outputs of the generators, maybe the elements of your power system. At the same time, it is possible that we can set our generator in such a fashion that we can achieve the minimum cost operation, and then it is called security constraint optimal power dispatch. So we saw that the various security monitoring and assessment functions, and we also saw that there's various here this functions, those are requiring some softwares. So the scheduling of the power application software functions, you can see here, it is the various functions. That the first one is your automatic generation control, and it is the average time that is computed on your IE86 CDAC platform of 217 nodes of Western grade. The automatic generation control functions, the average scheduling time is 2 to 3 seconds. Scheduling time. However, the average run time for this software is required 0.5 seconds. At the same time, we require the constraints economic dispatch. It is also called the optimal power flow study that requires 10 seconds of the run time. This is basically the CPU time. However, the average scheduling time requires 2 minutes because we have to change the settings of generator, etc. So that requires the fraction of minutes. We go for this other power application software functions, that is a generation reserve monitoring, that is also requires here 5 seconds for your average run time. Interchange transformer evaluation, that is a ITC evaluation, it may go for the 1 hour this average scheduling time, and average run time for this is almost 30 seconds. Another that is a very important function of energy management is that is your state estimation. Again, I want to say you the state estimation is the process where we estimate the states of the power system accurately in any noisy or erroneous environment. So for that we go for the several various a large number of information, we measure that, and that is passed through your telemetry, and finally it is coming to your state estimator. In state estimator, we have some computer software that try to evaluate the exact states of the power system. The average scheduling time for this is your 10 minutes, but its average run time requires at least 30 seconds. Other function is your optimal power flow. It is normally done on the request basis. It is if it is required, then only it is done, but its computational time requires at least 10 seconds. That is a CPU time. There is no elapsed time. Here it is a CPU, that is a computational time. So it is operator's power flow, which is every time it is required, whenever basically required, that is asked, and then it is done. Here again in the operator's power flow, there is a two type of power flow. One is your offline, another is your online. Online power flow is normally performed in the contingency analysis process. However, this your offline is whenever required you can do this study. So it is 10 seconds if it is a big system. In this optimal power flow are also it is known as economic load dispatch, and it requires 60 seconds. It depends upon again system to system. If your system is very large, its time may increase. Your contingency analysis, you know the contingency analysis is having several parts. One is the contingency evaluation, contingency selection, and then contingency ranking. Here basically evaluation is the last part. So the contingency definition, contingency ranking, and then we go for the contingency evaluation. So all these three processes included in the contingency analysis, and this requires at least 20 seconds for the average run time, but here for the average scheduling time is 15 minutes. We also require the short circuit calculation, and again it is again depends upon the system to system, and that calculation requires here your 10 seconds. Load forecasting. Again, the load forecasting can be done in the different fashion. Load forecasting can be of different type, whether it is long term, medium term, or short term load forecasting. Again, this short term load forecasting can be categorized at the various interval. It may be for 1 day, it may be hourly, it may be even though half hourly. We saw in the previous here section. Here we saw this, we require the load forecasting. Then this load forecasting within 30 minutes. However, other load forecasting here functions may require half an hour so that the operator can schedule the generating station accordingly. So it may require 4 to 8 hours for the average scheduling, but computational time is very fast requirement, that is a 20 seconds. We also go for the unit commitment. Unit commitment, that's turning on a unit, that is generating unit, or it is a shutting it off. So lighting on of any generating units may require several hours. Again, it depends on what is the state of your generator. Means if it is a cold roll or it is a hot roll. In cold roll, if it is a thermal coal-based power plant, then it may require 7 to 8 hours. However, in a hot roll, it may require 3 to 4 hours. So this unit commitment that we have to arrange, we have to commit the units so that we can achieve our economic operation. At the same time, we can also go for the maintenance scheduling of these generators so that we can plan accordingly. So these are the various computer of power application software functions and their average time. Now I can summarize here the various management function, means your energy management functions, EMS. First, that is very important, is your state estimation. Then we have a software related to economic dispatch. Here in the economic dispatch, there is a various type of economic dispatch programs, that it may be your real power dispatch, it may be your reactive power dispatch, it may be your emission. Nowadays, this is also very important, that we have to operate our power system in a such way that they should emit less environmental, those are polluting environment, you can say pollutants. So we can go for the minimum emission dispatch, we can go for the reactive power dispatch. In the reactive power dispatch, normally what we do, we try to minimize the system loss, the real power loss. However, in the real power dispatch, normally it is called the economic dispatch, where we try to go for the cost, minimize the cost of all the generating units in total. Another we require function, that is your supervisory control and data acquisition system. This is also known as SCADA, that is very important. So this SCADA, this is the supervisory control as well as the data acquisition system. We know the data we have to get it from the field, from the various units of the elements of the power system. Those are spread all over your geographical area. So we have to measure those data, and once these data are measured, then we have to transmit these data to your energy control function center where we can process it, and then from there we can go for some supervisory control. Here the SCADA is nowadays very important. Any measuring unit like your RTU, that is a remote terminal unit, it measures the data. At the same time, some of the functions it can do the supervisory control as well, and then other information it can send to the energy management function. Another function is your called AGC, means automatic generation control. It is also known as the load frequency control, automatic generation control, load frequency control. It is sometimes called primary, secondary and tertiary controls of the generating units, and we will see this automatic generation control much in detail in later modules. Here what we try to do, we try to set the power generations of the generating units so that we can maintain the frequency of power system. So this is your AGC. Another is your automatic voltage and the system control. Sometimes it's called automatic voltage regulator or automatic voltage control. In any generating power system, we have the two loops. A generator is equipped with your excitation system. That excitation system controls the voltage of the power system, of the terminal of the terminal of the generator voltage, and also it sets the reactive power output. In the AGC, as I said, we control the frequency of the system, and this frequency is the global in nature, means the frequency of whole system is the same. However, the voltage at the individual node, individual point is different. So automatic voltage control means we have to control the excitation of the generators so that we can achieve our system voltage profile, and thereby we can generate the reactive power. We always know this reactive power is directly related to your voltage, whereas your frequency is directly related to your real power. So if you are changing your real power of a generator, means you are changing the frequency of the system, whereas if you are changing the reactive power of the system, means you are changing the terminal voltage, means by vice versa, means you can change the terminal voltage, thereby the reactive power output of that generator will be changed. So in the automatic voltage control, we control the voltage of your generating units. At the same time, the system control is not the generator control, it may be the substation control, it may be we can use other devices in the power system to provide the reactive power support so that we can maintain our voltage in the desired limit. Other energy management function is your online power system studies. We require the various studies like your load flow, that is very common and very frequently used. Another is your short circuit calculation. We also sometimes require the stability. Studies. So these are your online studies. Those are performed whenever they are required. Another energy management function is your offline power system studies. These are also the studies similar to your online, but they are done offline. Means there is no need to every time online we have to go far, because it's a very time consuming process. Here calculation of short circuit, stability and the load flow. So some of the studies we can perform offline so that we can see the system performance, etc. for our analysis and other you can say monitoring purposes. So these are also including your load flow, your short circuit and your stability studies. Another energy management function that is very important is your security analysis and the monitoring. Already in the previous slide I explained you the security analysis and monitoring functions start from the measurement. Here you can see this is a security monitoring and assessment function which start from the measurement, and then we take the various control actions and then we operate our power system in secure manner. So this is your security analysis and the monitoring functions. Another is your automatic trouble analysis and the proving help to the system operator. We require various system analysis modules so that we can analyze the troubles of the power system. And at the same time, that will be very useful for the system operator to manage the power system in efficient, secure and the reliable manner. So these analyses are required so that we can analyze. For example, if there is some voltage dip somewhere in the power system, based on that dip, that information is coming to your energy management system, it is now your duty to know why this dip has occurred. It may have the different, even the problem later on. So this automatic trouble analysis may give you information what was the problem, where was the problem and how to mitigate that problem. So that will be very important for the operating your system in the efficient, secure and the reliable manner. Another is your automatic system restoration. We know there are some part of the system may be out due to the various faults, due to the various other contingencies in the systems. So we require the system restoration process. Again, if suppose your system is completely in blackout, what will happen? Then you have to light up your generators, because in the blackout means your generator has gone, transmission lines are tripped. So you have to start from one end so that you can synchronize your grid as quickly as possible. This is the main aim of the system operators, that the system must be restored in the as minimum time possible. For that, we must require the automatic system restoration procedures. Because it's a manual, it will require large time, and that during that interval you are not supplying electricity to your customer. That is a huge loss of the revenue and also huge loss of the customers. So automatic system restoration procedures are applied, and again it depends upon the various system to system. It is not unique, so it must be, there are some guidelines. At the same time, there are some procedures. Based on that, you can restore your power system in very efficient manner. Another that is very important of your energy management function is your emergency control. It is not always possible to run power system in the normal state, because there are so many events that are out of your control. For example, if you are having a transmission line, there is some lightning stroke over that line. What will happen? There is huge energy is flowing on the transmission line, and there may be possibility that that line will be tripped, and that may lead to the cascade tripping of the several lines as well as your generators. So in that, it is a fraction of time, fraction of minutes. In that, you have to take some actions so that you can restore your system. Main intention of this electricity operators, that we have to provide the supply with the less interruption to our customers. So we require the emergency control functions whenever there will be problem even though in generator station or in the substation station. Wherever there is a problem, we have to use the emergency control so that it should not lead to the cascade tripping, and that is called the collapse of the system. So the emergency controls are always there in the power system, whether it is a generating station or it is a normal substation, so that operator can take those actions to maintain the system, complete system or the part of the system, so that he can supply power in a economical, secure and uninterruptible way. Okay, now let us see the various hierarchical control structure of the power system, means how we operate. As we saw, the power system is very bulky in the sense that we have the various substations, we have various smaller and smaller units, and they must operate in the coordinated fashion, because it is not possible. Electricity is one of that. This electron, once they are flowing, they cannot be stopped in the intermediate lines. So once the power is generated, it must be going to the customer. Means we cannot store the electricity in the bulk amount of power. So the various control hierarchical structure process are adapted to provide a smooth and the reliable power supply to the customers. The first level, this here you can see this table where we have given here the levels, various levels, what are the various systems, monitoring and control here, what we are going to monitor, and the major functions of those levels. This hierarchical control structure of power system is known as bottom to top control hierarchy. Means the level first one is your bottom point, and then it is keep on moving to the fourth level, or you can say higher levels. So in first level, it is nothing but your generating stations and the substation controls, and it is also called the local control centers. For example, if you are having a generating plant, there may be one or two or several units, then you should have first one unit. If is there, then there will be one control unit for that individual unit. If you are having several such type of units, then all these units will have a one coordinated unit, so that there will be any problem, it can be sorted out locally. For example, you can see there is some problem in this BFP, boiler feed pump of a thermal power station. So that problem is the local problem. It is nothing with this your central dispatch center. So that problem must be sorted out with the local control structure itself. What are the various problems in that control? It must be taken care by the local operators, and that is called your local control center. Similarly, we have the various substations. Substations, maybe it is 400 kV substation, it may be 220 kV substation, it may be 132 kV substation, and so on and so forth. Now again, if you will see what is this substation, why we call it the 400 kV or 220 or 132 kV. Basically, it is the maximum voltage possible at that substation is basically the rating of that voltage of that substation. For example, if you are having a substation, there is a transformer, means some of the lines, if they are coming at the 400 kV, they are even the outside, if they are going 220 or 33 kV, that substation is called the 400 kV. Means the highest voltage possible in that substation. Means if you are having any equipment that is sustaining that highest possible voltage, then we say that voltage is the rating of the substation. Whenever you pass through any street, any road, any substation, you will find it is written like 33 kV substation. It is written 132 kV substation, maybe 220, maybe 400, and nowadays you can also find 800 kV substation. 800 kV lines are already constructed in our country, and it is very near to us. That is a Unnao substation. It is from Anpara Unnao line, that is designed at the 800 kV. So you will find 800 kV substation. Means we have some of the equipment there. I am not saying all, because some instruments, some apparatus there will be having the lower voltage. So highest possible voltage is the 800 kV, then we call 800 kV substation. So in that substation we have the various controls, and those controls are for the proper operation of those units. So the major functions of the first level control is, it is a prime mover control of generating unit. Here for the generating unit we are talking the excitation control of generating unit. We will discuss the prime mover control as well as the excitation control later on in other modules of this course. We have the generating station auxiliary controls. You know, in the any generating station we have a lot of auxiliaries. Auxiliaries means we have to have several auxiliaries for generating a single megawatt of power. For example, you know, in the thermal power station we have the boiler feed pump, we have the condensate pumps, condensers, we have the PF primary air fan, we have the FD fans, we have ID fans, we have the coal mills, ball mills. So several units, several motors, and they are equipped with various control, the individual control units. So here we require the various control functions, they are in that unit itself, and that must be performed, and that comes under the first level of your control of the power system. If you are, so all these three, first 1 to 3 is related to your generating plant controls. Means your prime mover, means you have to control the prime mover. What is the prime mover of your generating station? It is a turbine, and turbine gets energy in terms of steam from your boiler. So we have to control, and here normally it is called the governor control. Governors are there, so they try to increase the output of the turbine, and finally it is coming to your alternator and it gives the output accordingly. Excitation control, as I said, it is nothing but we have to set the voltage of the generating unit, terminal voltage, so that we can generate the required amount of reactive power. And the other auxiliaries, the various auxiliaries are used in the generating power station. Just I want to tell you, in the thermal power station, the 10% of the rating of a thermal unit is consumed for the auxiliary itself. Means if you have a 100 megawatt unit, means you require 10 megawatt power that is required and that is consumed in the auxiliaries of that generator itself. So it is 10%. However, in hydro it is less than 1%. It's very small because the auxiliaries are very less in the hydro. However, in the thermal it is very high. Thermal, maybe in the nuclear also, it is very high consumption for the auxiliaries. So we require the auxiliary controls for those things. In the substation, that is nothing but it is a transformers. There are transformers, there are the lightning arresters, there are reactors. So many elements are there in the substation, and those must be controlled locally. If they are controlled locally, then it is called the first level control. Second level control, now let us see. In the second level control, it is related to the area load dispatch centers, and normally it is called ALDC. So whole state, whole region is divided into the several ALDC centers. For example, in UP, it was the 4 area load dispatch centers, and Panki was one of them. Presently, it is one of them. So in the area load dispatch centers, what we monitor your the sub-transmission system and the transmission network. Means we can manage the load. So the major functions of ALDC is your generation and the load control. Means here we control the generation so that we can meet the demand. At the same time, here in the load control, we have to go for the load control as well, so that we can match generation and load together, so that we can maintain the frequency and we can operate our system smoothly. And also they get control as per instruction of third level. Now this is the third level control, means it is a state load dispatch centers. They give some information. For example, there is some line between, let's suppose, one station to another station, and they are getting the information, now trip this line. So sitting in the control room, they can trip that line. Again, the requirement why this line is to be tripped, again it comes from your third level. So the third level control, that is nothing but your state load dispatch center, and it is also called SLDC. So in each state, for example in UP we have one, that is one state. So we have one state load dispatch center that is situated in Lucknow, that is in Shakti Bhavan itself. So this state load dispatch centers looks after the overall operation and management of your states of UP itself. So the major functions are your system generation and the load monitoring and the control. They monitor what are the generation of the power system, how much they are going to generate, how much they generate in the next hours, or so on and so forth, and how the load will be monitored. Means they have to supply power to the loads. If they are unable, then they are going to set the load accordingly, so that the load and generation can be balanced. Basically here in our state, since always we are suffering from the crisis of power, so they are going to see the load management, because the generations are normally generating is your maximum level. So we are basically controlling the load so that we can match your generation as well as load to maintain the frequency of the system. So they normally look at the frequency. If the frequency is 50 Hz, they say they are very happy. If the frequency falls down, they are very much worried, and they will go for the load setting so that they can improve the frequency of the system. So it is functions regarding this state-wise monitoring and control. They also monitor all the things, and they get all the information, and that is used for the current operating scenario and also for the post-operating scenario. They get all the information, and those information are very much required for the post-operation as well as the present operating condition. So here already I have said this load shedding and the load restoration. If your system is some part of our complete system is in blackout, then you have to restore the system, and that policy is decided from the SLDC itself in that state. So they plan some restorative plans, and based on that we keep on connecting the various elements of power system, and so that we can provide the electricity in much less time. This SLDC is also responsible for planning and monitoring of the system operations. For the future planning, means future planning is not planning for the after 4 or 5 years, it is a planning for a day, planning for a month, or so on and so forth, and they monitor all the power system quantities, and then that information is used for your electricity board officials. Here they should also follow the instructions received from the higher level. Higher level means here for them it is fourth level, and they get the information from the fourth level to change their generator setting, to change the load setting, to change the transmission line status, means outage or intact system, and based on that they give this information to the various levels, means level number 2 or level number 1 accordingly. So they are the base, heart of individual state. They get information from this fourth level, and that information is passed on to the second and first level for smooth operation of the power system. Now let us come to the fourth level. Fourth level is basically the interconnected power system. As we know, we have various regions, and like we are living in the Northern Regional Electricity Board region, NREB normally we call it. In that the several states like your UP, Uttaranchal, Haryana, Punjab, Chandigarh, Himachal Pradesh, Jammu and Kashmir, they are interconnected. So each state is having one state load dispatch center. So we require some coordinated control for all these states, and then it is called NR, Regional Load Dispatch Center. This is RLDC. So we have the several RLDC, that is depending on the region. So we have NR LDC, that is a Northern Region Load Dispatch Center. We have Western Region Load Dispatch Center. We have Eastern Region Load Dispatch Center. We have Southern Region Load Dispatch Center, and we have another one, that is Northern Eastern Regional Load Dispatch Centers. So we have the various regional level load dispatch centers. Their functions are to integrate operation of the state load dispatch centers. So as I said, it is the integrating body. It gets information from the various states, and then finally based on the looking the various constraints, they give the information to the various state level load dispatch centers. So their other functions are operation and the maintenance of schedule of the generating units, transmission lines, etc. So various transmission lines presently, they are the inter-regional transmission lines, inter-state transmission line. So their operation, maintenance, etc. they normally monitor. They also monitor the control of the interstate and the inter-regional power transactions. As I said, all these states are connected. So we have the one regional load dispatch center. So there will be some power transfer, and that power transfer is monitored by these regional load dispatch center. Now in India we are going to have our national grid we are talking. Now all these regional load dispatch centers, means all the states are going to be connected. Most of them are already connected, like Northern is connected with the Western is going to be connected with the Southern. So whole this India is going to have one grid, and that is called national grid. So we'll have another level later, that is your fifth level control, and that is called your national grid, and then if that will be materialized, then our structure will be the different one. Here you can see all the levels. So this is your first level, this is your second level, this is your third level, which I explained, and this is your fourth level, and we are going to have the fifth level. And we start from, as I said, from bottom to top. So this is your generating units control, this is your distribution centers control. At the same time, we may have some transmission substation controls here. So all these are coming at the first level of the control. To recap, here these are the various generating plants, here the various distribution centers, and at the same times we have the various transmission substation centers. Now we have now the second level of control, that is here it is called ALDC. So this is area load dispatch center control. They control the power plant in that respective. They get the information from the state load dispatch center. It is your SLDC, state load dispatch center, and it is one in each state. And here in UP we have in Lucknow. And this ALDC will be several in the numbers. Presently we have the 4 ALDC in our UP. So they control the transmission plants, yes, transmission substation, and this your power plant, and finally they get information from the control centers, that is a state load dispatch center. And these state load dispatch centers, the various will be there for all the states, they get from the region, or you can say pool control center. It is also called regional load dispatch center, SLDC. And as I said, we are going to have this whole national, and that is called your national load dispatch center, that will be the top, and it is the supreme authority. So here the powers that if you will say that all these units must follow the instruction from their hierarchy. Means here this unit will get information from ALDC, or even though they can get information directly from the state load dispatch center, and they have to follow that, they have to do the action accordingly. Here, so this state is one state, and they are going to monitor. Normally here the RLDC, they never interfere in the individual operation of these load dispatch centers. Here you are the first level, R area load, or basically this is called your unit load dispatch centers of individual substation. They normally here NRAB, that is coming to the state level, and then they provide the information to the various units. So this is your control hierarchy of your power system. Now let us come to the recap of this module 1. Now in this module 1, I had 3 lectures. First lecture was basically devoted the first 2 points, that is the evolution of the power system with the significant milestone. We saw that our present day power system is highly complex, and it is integrated with both AC and DC transmission systems. However, the generation and the distribution, or you can say utilization, is the mainly AC. Now again, nowadays you can see now the DC use. For example, for use of the computers, we use the DC power. Again inside that, so we convert from AC to DC again for the various purposes. We also saw the structure of the power system, that we have generating stations at the different voltage levels. Then we have the generating transformers. Those generating transformers lift the voltage at the desired level, and then we have the interconnected power system comprises of different voltage level, that is both EHV as well as the high voltage transmission lines. Then we have the various type of other units, like the small units. Those are normally inside the distribution system, and then we can give the power supply to the various users at the higher voltage, lower voltage, as well as the medium voltage, and finally our customers, they are getting. So this power system structure that we follow from the generating stations, we must carry power over the GTs, then the transmission line, then distribution wires, and finally it must reach to our customers In the second module, what I explained you, I explained these 3 points. This point is basically common in your second as well as third lecture, but in the lecture 2, the importance of various power system interconnections was explained. We saw what is the advantage of interconnection power system. Interconnected power system has several advantages. At the same time, it has some problem, but the modern energy management system, those are very much automated, and based on that we can remove the various complexity of the interconnected power system. We also saw the design and operating criteria, and I elaborated there are the 5 design and operating criteria. First, I said the power quality. I said power system should be secure, it should be reliable, it should be economical, and it should be stable as well, because we must supply power in the stable and the efficient manner. So the various design and operating criteria I explained. I explained the power quality issues, those are very much emerging right now, and I also explained the various operating states in the power system for the security analysis, for the secure operation of power system. I explained the normal state, alert state, emergency state, restorative state, as well as the extremes. We saw the various state models, starting from the D'Eliaco 3-state model, then we saw Finks and Carlson 5-state model, and then very exhaustive model given by B. Stott et al., and we saw that in the lecture 2. We also saw this in lecture 2 some of the part, the nature of the various control actions like your preventive, emergency, and the restorative controls, so that we can operate our power system in the normal state, or you can say we can operate our system in the secure way. In the today's lecture, just I discussed the 2 major points. One is your modern energy management functions, and second one the hierarchy of control and their coordination. In the modern energy management functions, we saw the various functions starting from the measurement of the data, that is RTU, SCADA functions, that is we are measuring the data, finally we are transmitting data over the telemetry unit, and it is finally coming to your state estimator, where we estimate the states, and thereby we analyze the current state of the power system. If it is in the some normal state, then we can go for some other actions. If it is not in the normal state, then we have to take some preventive, some corrective actions for the emergency as well as the restorative controls. We display alarm as well, and then if it is in normal state, then we can go for the security analysis, economic dispatch, and then we can go for the AGC, etc. So I explained the various modern energy management functions along with the what is the approximate execution time for the various functions as well. And the last which I explained the hierarchy of controls and their coordination. I gave the various control levels starting from bottom to the top in the state. That is, in state we had the 3-level control. First one is the unit level control, then we went for the area level control, and finally it is the state level control. Now we have the 4th level control, that is the region level control, means regional electricity boards are there and the various states are interconnected and their roles and responsibilities were explained. Now again we are going to have the national level, that is a 5th level control. Once all this REBs, regional electricity boards, will be interconnected, then we can have your complete power system 5th level control. So in India right now we have the 4-level control, and then we are planning to the 5th level control as well. So it is at end. Now you have understood the power system, the structure, operating and designing criteria, and their control hierarchy. Thank you.